Hello again. We're going to take a look at section 11.2, which is going to extend our um, knowledge of probability. It's going to allow us to practice in a different setting. And specifically, we're going to be concerning ourselves with the probability of something not happening or the probability that either this happens or that happens. And so relatively small in scope as we go into this next section. It's going to add a little bit more onto our repertoire. So what we got out of 11.1 is how to find basic probability, and they also introduced the idea of odds. And what we're going to get out of this one are another two types of concepts there. And so one of the things that it wants us to remember is that probabilities, and they use this symbol, probability event E, um, it is a number that is no more than 1 and no less than 0. It absolutely can be either one of those, though. For a probability of an event being 0, we know that that means that it cannot happen. So let me be even more specific about that. E cannot happen. So if we said something like the probability that someone in our class is not registered with Los Rios, the probability of that would be 0. You all are registered. And so, and it's an example of the not right there. So the not just means the opposite of that. They'll also remind us that the probability of an event equaling 1 is meaning that E is going to happen. Right? It has to happen. It's a sure thing. So the probability that someone in our class is registered with Los Rios is 1. The probability that when you roll a six-sided die that a number between 1 and 6 comes up is 1. And so they're just reminding us about those properties as we enter into those sections. But what's important for us is to realize that that if the probability of E is equal to 1/4, then we know the probability of not E. Not E has to be the total opposite. So if you remember what the probability was, it was the number of ways something could occur all over the total number of possible outcomes. And so if we look at the probability of E, I'll underline it right here. It's saying that there's one way out of 4 for that event to occur. So the probability that it doesn't occur is 3 ways out of the same 4 total ways. Notice that the probability of E and the probability of not E. Actually, they're not using that notation in our book, so let me be careful there. The probability of E and the probability of not E, they always have to equal 1. So in particular, if you want to find the probability of not E, well, that's 1 minus the probability of E. So if I told you, you're used to this, if I told you that there was a 70% pass rate in a class, could you tell me the fail rate, the probability that you don't pass, right? So percentages and probabilities are pretty much the same thing. So this is saying the probability that you pass is 0.7. So the probability that you do not pass, or what we sometimes call fail, is 1 minus 0.7, like you've probably already done for 0.3. And so the probability that someone does not pass or fails is 30%. And so we're kind of used to this already. And so you'll see some questions that are like that. The other questions that will be there are dealing with the OR probability, and they give you a formula. And I don't know, sometimes people live and die by formulas, but I'll teach the formula just to have it to reinforce what's in the book. However, I think it's better just to think through some of the situations. And so the other thing that they're going to do is they're going to say, hey, what's the probability of event A happening or an event B? As they do so, on page 620 of your textbook, they're going to talk about mutually exclusive events. And they'll say this: two events are mutually exclusive. Sorry, I'll spell that right. If they have no outcomes in common. And we're going to want to know whether events are mutually exclusive when we ask the OR probability. So let me give you an example that's not in the book or anything. I'll just make it up. And that is a student in our class and someone with brown hair. Okay. So if I said find the probability that if you gather together all the Math 300 students, and I'll write that out, find the probability that all Math 300 registered students let me say this, that if one person, I'll make that look a little bit better. I'm realizing I'm asking the question in a way that backboxes me into the corner. Find the probability that if one student was randomly selected from all registered Math 300 students in the district, that the person would either be from our class or have brown hair. Okay, so I'm making something up that's a little bit obscure, but because I think it will allow us to think a little bit and not be boxed up into some small situation where we're trying to see things. So we obviously don't have the demographics of everybody that's taking Math 300, but the question is, could these, when you ask the question about mutually exclusive, let me roll down to the definition. You want to know about if two events are mutually exclusive when you ask an OR probability. Let me come in here and highlight that. Oops. Go backwards and then let me grab that highlighter. This is into play when you have OR. Every time you have an OR probability, the way our book's presenting it, you want to know if the events are mutually exclusive. And they're mutually exclusive if they cannot happen at the same time. So, a student in our class and someone having brown hair. This would be mutually exclusive only if no one in our class had brown hair. Okay, I'm sure someone in our class does. Therefore, the events are not mutually exclusive. They could happen at the same time. With one pick, I could get someone that's from our class and has brown hair. That's a problem, because the problem is I don't want to double count them. The formula that they present in the book is this: the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And let me tell you what this means. So for us, A is a student in our class. So we want to know whether the person's a student in our class. I'll just put our class. And B is conveniently brown hair. So A represents our class because everybody's going to get an A. B represents brown hair for obvious reasons. So what they're saying is if you want to know this probability, one way to figure it out is take the probability of randomly selecting someone from our class. Well, we have 25 students in our class, and let's suppose that there's 3,000 students that are taking Stat 300 across the district. The probability that somebody's going to be from our class is 25 out of 3,000. Then we got to add to that the probability that the person has brown hair. Again, there's 3,000 individuals, and for lack of a better reason, let's suppose 1,000 of them, a third of them, had brown hair. So I'm totally making that up, but just for emphasis. So I hope you can picture that. You're looking at the entire group of Los Rios students who are taking Math 300. 25 of them are in our class. That number I know for sure. And then let's assume that we've counted that 1,000 of them have brown hair. This wouldn't be the right probability. The right probability is not 1,025 over 3,000 because it's not mutually exclusive. Because it's not mutually exclusive, I have to subtract out from the 3,000 those that I've double counted. These are the people from our class that have brown hair. So they're in our class and have brown hair. I've counted them. The reason why we have to do the subtraction, so let me highlight that in a different color. Let me highlight that in red. The reason why we have to subtract out is because we counted them once here and once here. We counted them as students in our class and we counted them as brown-haired individuals. So we got to back them out once because they've been counted twice right now. So let's suppose in our class there's 8 students with brown hair. So that's going to give us the probability where we take the probability of the person being from our class plus the probability of anybody having brown hair minus the probability that are from our class and have brown hair. If they are mutually exclusive, if they cannot have the same outcome in common, then we don't have to do that subtraction, and they show that formula too. It's just simply the probability of A plus the probability of B. So they're trying to give it a formulaic type of approach. You're welcome to use that formula on the exam. You can come to the exam with the book or whatever you need. And so that's what we're looking at doing in this section. If I look at the homework exercise set and see what we have, let's roll some dice. For the experiment of rolling an ordinary pair of dice, find the probability that the sum will be the sum will be each of the following. You may want to use a table showing the sum for each of the 36 equally likely outcomes. So you've probably done that in the first section. I'll keep the red pen. There's 1, 1, 1, 2. I might have done it in a video. 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, all the way down to 2, 6, and 6, 1, 6, 2, 6, 3, all the way down to 6, 6. Those would be the 36 outcomes, right, that kind of span that 6 by 6 grid. And so the question that they're asking is in number 18 in our textbook, right? You have the online homework, but let me look at number 18 in our textbook, and I'll switch over to a different colored pen. But it's asking for this: find the probability that the result is 11 or 12. So the first question to ask is, are they mutually exclusive? Is it possible in a single roll of the die, in a pair of dice, single roll of the dice, to get an 11 and a 12 at the same time? So picture one roll of the die. And the answer to that is no. It's either going to show 11 or show 12 or show something different, but it's not going to show both 11 and 12 at the same time. So we don't have to do any subtraction. We've determined that they are mutually exclusive. that they cannot happen at the same time. Therefore, we will just count it up. So what are the ways that we can get an 11? We can get an 11, and let's think about that. I think in only two ways. The only way to get an 11 is 5, 6, and followed by 6, 5. 4 doesn't work because it would need to be matched with a 7, which isn't on our die. And so we're not thinking about that at all. So for the 11, there's two ways out of the 36. Remember, we're doing the probability of 11 plus the probability of 12. We're just following that formula. The probability that it's 12 is just one way out of 36. The only way to get a 12 is 6, 6. And the two together is 336, and they'll want us to reduce to 112. So that should be the answer that they have reflected in the back of the book, right, if we had those answers. Compare that to something that's right before it, number 17. Find the probability that we get an even number or a multiple of 3. So an even number, there's going to be lots of even numbers. And it may not be half. I don't know if we can assume that. So we'd have to kind of just methodically go through and say, okay, what are the ways that we can get an even number? So let me focus on the evens. The even numbers, 1, 1 would produce a 2. 1, 2 would produce an odd. 1, 3, not 1, 4, 1, 5, not 1, 6, 1, 7. Oh, there is no 1, 7. Look at me go. Okay, already making weird statements. Okay, so then when we go to 2, not 2, 1, but 2, 2. Then not 2, 3, but 2, 4, and 2, 6. And then we'd have 3, 1, 3, 3, 3, 5, 4, 2, 4, 4, 4, 6. Sorry, I almost jumped to the end. 5, 5, 1, 5, 3, 5, 5. Right, but not 5, 4 because that ups to be 9, and then 6, 1, 6, 2. Ooh, not 6, 1, 6, 2, 6, 4, and 6, 6. So there's 1, 2, 3, 6, 9, 12, 15, 18 ways out of 32 to get an even number. Okay, 18 ways to get an even number. So remember what we're doing. We're doing the probability of even plus the probability that it's a multiple of 3. Let's go find our multiples of 3. What are our multiples of 3? Well, 3 is, well, what are ways to get a 3? That might be the best way to handle this. Ways to get a 3. 1, 2, 2, 1. Then we'll go to 6. What are ways to get a 6? 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. 9. What are ways to get a 9? Not 1, not 2, but 3, 6, 4, 5, 5, 4, 6, 3. Sorry about that. 12. Only one way to get a 12. 6, 6. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 ways. I put a 32 under here. Should have been a 36. That might have caused you some confusion. I'm not sure where I came up with 32 other than being human, right? We do that sometimes. 12 out of 36 are there. We shouldn't be shocked that half the numbers, half the results are even, the other half would be odd. And so that's not shocking for us at all. Multiple of 3, 12 out of 36. And here they are, right? The 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 options that I have off on the left-hand side of the screen. But these are not mutually exclusive. They can happen at the same time. They have overlaps. So what were the overlaps that they have? Well, let's look for the overlaps over here on the left-hand side. And then I'll highlight. Sorry, I'm going to keep getting this message about my iCloud storage being full. I should try to fix that. Let me use a red marker. 1, 2, and 2, 1 are not, they're multiples of 3, but they're not even. 1, 5 is even though. 2 4 is even, 3 3 is even, 4 2 is even, 5 1 is even. And what you'll see is you'll see them as outcomes over here. And that's what they mean by mutually exclusive, that they're mutually exclusive only if they don't have the same outcomes. That was happening with the 11 and the 12, but here they have the same outcomes. They're not mutually exclusive. None of these here that made 9 are overlaps at all. But this is an even number of 12. So we have 1, 2, 3, 4, 5, 6 that have been double counted. They've been counted once as even results, and they've been counted a second time as multiples of 3. And so we would add those up. 18 and 12, that's going to give me 30 minus 6. That's 24 out of 36. And if we think about that, those are both multiples of 6, right? Actually, even stronger than that, multiples of 12. So we could pull out a 12. So if I divide by 12, I get down to 2 over 3. And that's the probability of the result being even or a multiple of 3. So I just wanted you to have kind of within my own language what this section's topics were. So hopefully that's helpful as an augmentation to the videos that you're seeing through the MyMathLab, and also the online textbook, right, and other resources that you may be using. All right. Have a good day.